So in this video, I introduce the derivative function, and I talk about when it exists and when it doesn't exist. So given a function and a point x0 in its domain, we define the derivative f prime of x0 of this function at that value. It's just the slope of the graph at that point. It was also the rate of change of the function for that particular x value. We can now investigate the derivative then as a function in its own right, because we're really associating an x value, x0, with a slope. That's a function. So the derivative of the function f of x with respect to x equals f prime of x, and it's equal to this limit. Notice all I did was replace the x0 with x, because now we're thinking of that as a variable. The domain of the derivative then equals the set of all real values, just so that limit exists. We will say that the function is differentiable at an x value if and only if the derivative exists at that value, which means that the limit therefore exists. We'll say that a function is differentiable on an open interval if and only if the function is differentiable for every single x value in that open interval. It's differentiable in general if it's differentiable for every single value in its domain. And sometimes we might even mention differentiability on closed intervals. The only difference there is that for the endpoints, we insist that the limit is from the right or the left to make sure that we stay within the closed interval at all times. For example, let's go find the derivative of this function. Now we already know how to do so. It's just the only difference will be is that when you go about doing the computation, remember that x is actually in the limit itself, not actually a variable. The only thing changing the limit is the h. So we have the limit of f of x plus h minus f of x, and that's divided by h. So that then would equal the limit as h approaches 0 of, well, let's see, evaluating that function at x plus h, that would then be x plus h, that quantity squared, minus 2 times x plus h, and then be plus 5. And from that, we would then be subtracting the function at x. So that would be x squared minus 2x plus 5. And this entire quantity is then divided by h. Oh boy. So let's go ahead and simplify that. That then equals the limit as h approaches 0. Multiplying out or distributing all these products, you would then have x squared plus 2xh plus h squared plus, minus 2x minus 2h plus 5. And then I'd have a minus x squared, a plus 2x, and finally a minus 5, and that's all over h. So that would then be the limit as h approaches 0 of, in the numerator, the x squares cancel, the minus 2x plus 2x cancel, the plus 5 minus 5 cancel, leaving me only a 2xh plus a h squared minus a 2h divided by h. Notice though that since the limit is as h approaches 0, h isn't 0, and I can cancel those h's. So that would give me then a 2x plus an h minus 2, and I'm taking the limit of that expression. Remember, x is a constant. So that's actually a linear function in h. So that being a continuous function, I can find the answer by just plugging in 0 to get 2x minus 2. And that's it. That's the derivative. That then gives me the slope of that graph at any single x value along that graph. So in particular, if I want the equation of the line tangent to the graph where x is -1. So to find that, I know that the x value is -1. The y-coordinate of the point tangency is just f at that x value. That is f at -1. And that would be 1 plus 2 plus 5. That is 8. The slope would then be the derivative evaluated at that x value. And we know that now is -4. So the equation of the line is y minus the y-coordinate is equal to the slope times x minus the x-coordinate. That's it. That's the equation of the line tangent to the graph at that particular x value. Now, a clever little thing is is that you can find other ways to write the difference quotient. It's just a change in output over a change in input. So another way to do so is to take the limit of the change in the function value over the change of x as the change of x goes to 0. So then if you say that the z, being an x value, is approaching x, being an x value, that difference would then be the change of x, z minus x. The numerator then would just be the difference in those function values, f of z minus f of x. Notice in that limit, all the z's would disappear, because in the end you would plug in for x. Let's go ahead and use this alternate form to find the derivative of f of x equals x squared. So in that case, the derivative would equal the limit as z approaches x of f of z minus f of x all over z minus x. That is the limit as z approaches x of z squared minus x squared divided by z minus x. But notice, you could then factor the numerator and cancel a common factor to get z plus x. That is a polynomial in z. Z is the actual variable changing. X is constant. So that's certainly a continuous function in z. So I just plug in x for z to get x plus x, which is 2x. So the derivative of x squared in terms of x must be 2x. Now the reason I brought that up is it's actually kind of convenient to look at the derivative using different notations. So for example, what if you want to know the derivative at only one x value? Then all you need in the denominator is a change in x values, let's say x minus x naught. And the numerator, you need the corresponding y values and take their difference. That way you'd still preserve the difference quotient, the change in the y's over the change in the x's. And then you just make sure the change of x goes to 0. So if I wanted to know, is the function f of x equal to the absolute value of x? Is it differentiable at 0? We can just check the limit. So f prime of 0, if it's going to exist, it must be the limit as x approaches 0 of, you would have f of x being the absolute value of x minus the value of the function at 0 all over x minus 0. So you recognize that as the limit as x approaches 0 of the absolute value of x over x. This is one of those limits I actually did before. We know that this limit, in fact, doesn't exist. If you don't recall, it's because you need to take the limit of this function as x approaches 0 from the right. And in that case, you can replace the absolute value with what's equivalent to for this range of values, which is just x, because it's already positive. So that would then be the limit of just 1. So that answer is 1. But if you take the limit of the exact same expression as x approaches 0 from the left, well now, if x approaches 0 from the left, then x is negative. And the only way to make it positive is to take its opposite. So for negative values, the absolute value of x is equivalent to negative x. That limit, on the other hand, is negative 1. Those two limits are not the same. So since the limit from the left and the limit to the right don't agree, there is no limit, which means there is no derivative at 0. There is derivatives everywhere else, just not at 0. So this function is considered to be not differentiable because it's not differentiable for every single value in its domain. Notice, do you see the sharp corner in the graph? That's what's happening here. It's almost like that to one side, the slope wants to be 1, and to the other side, the slope wants to be negative 1. So there isn't a single slope at that point. Let's consider a new function. The cube root of x winds up being differentiable pretty much everywhere but at 0. And the easiest way to see that is just, once again, to crank out the limit. So if we take the limit as x approaches 0 of the cube root of x being the function minus the cube root of 0 all over x minus 0, that would then be the limit as x approaches 0 of, that would be the cube root of x all over x. And you should recognize that as the same as saying the limit as x approaches 0 of 1 over x to the 2/3 power. This limit then, if you take either limit from the left or the right, that limit does not exist, but it is unbounded. And it's in both cases going to positive infinity. So this limit doesn't exist, but it is infinite. This is an example where at a single point, you have a tangent line, but it's vertical. So because of that, it's considered to be a non-differentiable function, at least at 0. The function is differentiable everywhere else, just not at 0 itself. So there's a third way that a function would not have a derivative, but it has such a nice other result that it's something we really should prove. So I'm going to assume that we have a function, f of x, that is differentiable at x0. I'm going to show you this particular limit here is 0. Now, I'm going to restrict myself only to the limit laws and being clever with limits. So, notice that since x is not x0, I can divide and multiply by x minus x0. Then I'd have the limit of a product. But the limit of a product is a product of limits. The limit of the first factor you should recognize as the derivative of the function at x0, while the limit of the second factor in that product, that's just the limit of a polynomial. You just plug in x0. But that limit would then be 0. So this limit should equal f prime of x0, which is a number, times 0, and that's 0. Okay, let's try it again. I'd like to know what's the limit of just f of x as x approaches x0. Well, in each of these two limits, I'm sure a few of you were expecting me to do, let's just plug in x and replace it with x0. That'll give me the result instantly. But that uses continuity. And we don't know that this result or these functions are continuous. We only know it's differentiable. So, again, being clever, define the limit of f of x as x approaches x0. That's the same as doing this limit. I'm just adding and subtracting the exact same constant, which I know must exist because the function is differentiable. And in the definition of differentiability, you have to have f of x0. So, then that would then become a limit of a sum. So that's a sum of two limits. But the first limit, we know what that is, that's 0. And the second limit is a limit of a constant, that's just the constant. So we get that this is equal to just the constant. Looking at the beginning, the limit of f of x as x approaches x0, and looking at the end, it's equal to f at x0. You notice that I just showed you that the function must be continuous at x0. That's the result we really wanted, which was anytime the function is differentiable at a value, it's also instantly continuous there. What's really nice is the contrapositive, that if the function is not continuous, it's also obviously then not differentiable there. So those last three results were so useful that it's probably a good idea to re-emphasize them. So 3 typical ways that a function would not be differentiable would be that it's just not continuous there. Instantly then not differentiable. There is no slope at that point. You could also have a vertical tangent line to the curve. In that case, if there was a derivative, it'd have to be the slope of that tangent line, but there is no slope of a tangent line. So therefore, not differentiable. And the last one is that the graph has a sharp corner in the graph. If that's true, it's almost like there can't be one tangent line. To one side you have one slope, to the other you have a different one. So once again, without a single slope, the function cannot be differentiable at that value. So it's a good idea at this point to lay down some notation. If we ever say the function, we might write a bunch of different ways. We could write f of x, we might just say y, and it's assumed to be y is a function of x. We might even be explicit and write y with parentheses, x inside, to say y is a function of x. In terms of the derivative, we could then write f prime of x, we could write dy dx or df dx, we could write y prime of x, or just y prime. These are all the actual function, the derivative of the function in terms of x. If we want to evaluate that derivative at a value, we then use these notations usually. It's f prime of x naught, that's a derivative at a single x value. Dy dx or df dx, bar, that means evaluation, at x equals x naught. And the last one is y prime of x naught. All these cases are numbers. These all represent numbers. They're just the derivative at a single value. And lastly, you could also, for later on, we need to have notation to say, let's now take the derivative. This is the process of finding the derivative. We call this the differential operator. It's d over dx. It's just a bookmark to keep track of where you are while you're differentiating a function. So you can have d dx of, usually square brackets for me, put the function inside. You might even see d dx of and just put a y. That is the derivative of y in terms of x. It's just the act of finding that derivative. And that gives you a basic introduction to the derivative function. Now I've given you 4 facts here. One is the definition of the derivative as a limit of a difference quotient. Another is I gave you different ways to look at that difference quotient. Is just make sure that the limit is always so that the denominator is going to 0. And then third, 3 different ways that a function would not have a derivative at a value. And fourth, that differentiability at a value implies continuity at that same value for a function.